Good afternoon. My name is Jason Pick. Thank you for joining us today to discuss advanced fertility and fall applications on turf grass. To begin, I'd first like to remind everybody that a good fertilizer program begins with taking soil tests. It's always important to determine what your soil needs before we start deciding what kind of nutrients we should put down, or most importantly, how much money we should spend on fertilizer before we apply it. For those of you familiar with the pH chart, on the bottom right hand side, you'll see the available nutrients that we have based on our pH. Here in Alberta, we're quite predictable. With a little bit higher pH, you'll see that the availability of manganese, boron, and copper, as an example, are less available. Subsequently, those are the kinds of micronutrient additions that we need to add to our macronutrient program. Nonetheless, before you start making fertilizer decisions, diagnose that availability, determine your soil pH, and remember that regions are often a little bit predictable. So plan ahead and send your samples into the lab. Now, at the very basis of our conversation here, we know that nitrogen affects top growth, potassium affects crown, that's the growing points, and phosphorus affects root growth of our turfgrass plant. Now, the role in nitrogen, or the role of nitrogen in turfgrass, is the most important. All our fertility programs are based upon the usage of nitrogen, so we look at that first. As you may know, nitrogen increases shoot growth and also density. It also helps root development in conjunction with applications of potassium. Most of us will apply nitrogen kind of on an as-needed basis because our nitrogen also plays a strong role in recovery. So if you are working a very busy sports field or busy golf course and you need a little more recuperative help, nitrogen will help you there. So when we feel a little bit chlorotic, your turf feels a little bit stressed from all the traffic, applications of nitrogen can help us recover. Of course, it does promote color. The expression of chlorophyll in the plant shows that it's photosynthesizing and working, packing carbohydrate and building energy. The goal of our nitrogen tissues should be roughly between 3 and 6%. Nitrogen is very mobile in plant and soil, and as I mentioned, it is considered a macronutrient. Now, phosphorus, as you recall, is involved with root growth. Now, we mine phosphorus at the surface. Generally, phosphorus is found close to the surface, as opposed to deep mine like potassium. Phosphorus is very, very important in transferring energy as well as early root development. That's why when we buy starter fertilizers that has, for instance, analysis of 12, 24, 10, 24 being the phosphorus number or percentage of phosphorus in that bag, that's to encourage establishment and motivate seedling germination. So as a general rule of thumb, and this is according to Nick Christian's, half a pound of phosphorus every 1,000 square feet on a bi-weekly basis is a good rule of thumb for establishing new turf or recovering some of those center lines that have been so beat up. Now, potassium is used also in large quantities. Nitrogen, NP, and K, those three macros are used predominantly the most of all the 13 that we require. So it's second only to nitrogen, and it actually works the same way in nitrogen in that it will leach out just the same as nitrogen will. It dissolves just the same, essentially working precisely the same way a nitrogen does. So that's why when we talk about a balanced fertility program, we balance applications of nitrogen and potassium the same. Potassium is an important component in carbohydrate production, encourages rooting and wear tolerance and cell strength, also enhanced drought and cold tolerance. And we'll talk about that a little bit later towards the end of the presentation, about that relationship between nitrogen and potassium. It's a key component in cell wall development, and as I mentioned, also a macronutrient. Now, in addition to the NP and K, we have secondaries, or micronutrients. Some are secondaries, such as sulfur, calcium, and magnesium, and micronutrients: boron, sodium, manganese, iron, copper, silicon, and zinc. So applied in small amounts, micronutrients, we don't typically plan them or schedule them like we do the macronutrients, talking about a pound at a time. These are hundredths of a pound in micronutrients. Often they're added into your fertilizer blend and kind of work in the shadows. So regions, as I mentioned, has an impact on which micros are available. So our local regional suppliers know this already, and will typically tailor fertilizer programs based on region. So they can also be added as a foliar treatment, liquid solubles into foliar programs. Again, something we'll talk about a little later into the presentation. Now, when we talk about fertilization and fertilization programs, it's important to note that the reason for our decisions are not based so much on volume as they are based upon losses. Now, nitrogen uptake is actually only between 40 and 70%. Due to the immobilization, volatilization, leaching, and denitrification process of nitrogen application and the microbes that form these changes, we want to try to minimize these, obviously. So our efforts to getting the most for our money, or maximizing the availability of available forms of nitrogen in the soils, is really should be centered around our efforts to avoid all these losses. So that's what we're going to talk a little bit more about today. Some of the ways we can minimize losses: realize that nitrate and ammonium are the two only sources that plants can use that nitrogen without having to be converted by bacteria. Nitrifying bacteria, called nitrogen fixers, can make that ammonium and nitrates available to the plant. As I mentioned before, we need to apply these things in order for our surfaces to recover from stress and traffic and whatnot. So nitrate and ammonium nitrate being a great option as far as nitrogen application, in order to avoid some of those typical ways we can lose it to the environment and into the soil. For the next few minutes, I'd like to show you a video of the nitrogen cycle, which I think animates the process much better than I could explain.
Transformations of fertilizer nitrogen in the soil. Nitrogen, when applied to soil, undergoes transformation processes before becoming available for plants. The following animation explains the soil nitrogen cycle for two different sources of nitrogen: ammonium nitrate and urea. First option: nitrogen transformations when applying ammonium nitrate. Application of fertilizers containing mineral nitrogen as ammonium and nitrate. Organic fertilizers contain mostly complex forms of nitrogen and ammonium. Uptake of nitrate is rapid due to the high particle mobility. Most plants therefore prefer nitrate over ammonium. Uptake of ammonium is slower than that of nitrate. Ammonium is bound to clay particles in the soil, and roots have to reach it. Most of the ammonium is therefore nitrified before it is taken up by plants. Nitrification by soil bacteria converts ammonium into nitrate between a few days and a few weeks. Nitrous oxide and nitric oxide are lost to the atmosphere during the process. Denitrification is favored by lack of oxygen, for example due to waterlogging. Soil bacteria convert nitrate and nitrite into gaseous nitrous oxide, nitric oxide, and nitrogen. These are lost to the atmosphere. Immobilization transforms mineral nitrogen into soil organic matter. Activity of soil microbes is mainly stimulated by ammonium. Immobilized nitrogen is not immediately available for plant uptake, but needs to be mineralized first. Mineralization of soil organic matter and manure releases ammonium into the soil. Ammonia volatilization occurs when ammonium is converted to ammonia and lost to the atmosphere. A high soil pH level and temperature favor conversion of ammonium to ammonia. If conversion takes place at the soil's surface, losses are highest. Leaching of nitrate occurs mainly during winter and fallow periods when percolating rainfall washes residual and mineralized nitrates below the roots zone. Accurate fertilization increases nitrogen use efficiency and reduces the risk of leaching during the growth period and afterwards. Second option, nitrogen transformations when applying urea. Application of fertilizers containing nitrogen as urea. Organic fertilizers contain mostly complex forms of nitrogen and ammonium. Hydrolysis of urea by soil enzymes converts urea into ammonium and CO2 gas. Depending on temperature, hydrolysis takes a day to a week. The soil pH around the urea granules strongly increases during this process, favoring ammonia volatilization. Ammonia volatilization occurs when ammonium is converted to ammonia and lost to the atmosphere. A high soil pH level and temperature favor conversion of ammonium to ammonia. If conversion takes place at the soil surface, losses are highest. These conditions are met when urea is spread and not immediately incorporated. Nitrification by soil bacteria converts ammonium into nitrate in between a few days and a few weeks. Nitrous oxide and nitric oxide are lost to the atmosphere during the process. Uptake of nitrate is rapid due to high particle mobility. Most plants therefore prefer nitrate over ammonium. Uptake of ammonium is slower than that of nitrate. Ammonium is bound to clay particles in the soil and roots have to reach it. Most of the ammonium is therefore nitrified before it is taken up by plants. Denitrification is favored by lack of oxygen, for example due to waterlogging. Soil bacteria convert nitrate and nitrite into gaseous nitrous oxide, nitric oxide, and nitrogen. These are lost to the atmosphere. Immobilization transforms mineral nitrogen into soil organic matter. Activity of soil microbes is mainly stimulated by ammonium. Immobilized nitrogen is not immediately available for plants' uptake, but needs to be mineralized first. Mineralization of soil organic matter and manure releases ammonium into the soil. Leaching of nitrate occurs mainly during winter and fallow periods when percolating rainfall washes residual and mineralized nitrates below the root zone. Accurate fertilization increases nitrogen use efficiency and reduces the risk of leaching during the growth period and afterwards. In conclusion, ammonium nitrate is taken up directly by plants, while urea first needs to be converted. Ammonium nitrate therefore offers a higher nitrogen use efficiency than urea. Ammonium nitrate thus reduces losses and environmental impact.
Well, I hope you enjoyed that video. As I said, I think it illustrates the nitrogen cycle a little bit better than I could have explained. So thank you for your patience there, and hopefully this video is available to you afterwards. The next thing we're going to talk about here is the different types of nitrogen fertilizer available to you out there. The two main types are slow-release nitrogen and controlled-release nitrogen. Now, slow-release nitrogen is more of a natural approach, requiring microbial activity to break it down. Requires a little more hot, wet weather, a more natural release in general. Some of those different types you might find is ammonium sulfate and methylene ureas, which create those long nutrient chains that take a little longer the chain, the longer it takes for the microbes to break down, and therefore longer release. So on the other side of that coin, we have controlled release, and these are far more manufacturer type in terms of coatings and whatnot. You know, in the good old days, we were smart enough to try sulfur. That was a slow release nitrogen, controlled release product. Since then, we've come into polymer coats, plastic essentially, that breaks down, relying on moisture as well, but a little more predictable and stable. The problem that we always had with the sulfur coats were they were physically broken down. And also, if we got an unknown or heavy rainfall event, we would risk losing the whole thing. You can imagine, you know, my distaste about 20 years ago when I started using sulfur coat ureas. You put down a month's worth, and then it rains for 3 days, and everybody on the crew is mad at you because they're baling hay for the next 2.5, 3 weeks. So we've come a long way since the sulfur coats, and now the polymer coats are give us a little more control. Anywhere from 10 to actually 16 weeks, the urea diffuses in the soil by osmosis. Water gets taken in, which then again releases the nutrient. So a little bit less reliant on temperature, but more reliant on moisture, which ideally, depending on our situations, we should be able to control. Now, the nitrogen, phosphorus, potassium coatings are quite ranged. We can create as big of a coating or as long as a coating as we like. Usually, that release is specified by the manufacturer. There are golf courses out there that have applied one 16-week release, which is essentially one application for the entire summer, which is a great way to save labor. On the other side of that coin, if you do happen to have a big rainfall event, or for my situation, when our resort or property was trying to save money and asked how I could help, I wasn't much use if I had already put down 4 months of fertilizer, as opposed to saying, hey, I'll extend, or I won't put this much down, or whatnot. So that's completely up to you how you want to consider using some of these control releases. But anyways, on the manufacturer's bag there, it'll tell you what the release is percentage-wise. For example, a 16-week release will release its entirety over that 4-month period. But it'll also usually have a small percentage of immediately available. So, like in my past, I would usually try to stretch my fertilizer application as long as I could. So when I started to see some chlorosis, a little bit of yellowing, I knew it was time. I wanted to, when I decided to finally put fertilizer down, I kind of needed a bit of a kick right off the get-go to catch up, so to speak, from that visual chlorosis. So quite common for you to find a fertilizer product, a CRN polymer with 75% slow release, 25% immediately available, which will give you that initial kick right after application. Now there's also nitrogen additives that we can apply to our products that slow our losses. One which slows the rate of hydrolysis, that is, it slows the rate of that product to absorb water, which in turn slows the rate of potential volatilization. On the other side, we also have additives which inhibit bacteria. Now, as we know, the denitrification process involves microbes breaking down that nitrogen additive and making it unavailable. So what the DCD does is it inhibits that bacteria from breaking it down as fast, therefore slowing the rate of denitrification into the gas. So that's some of the products that you'll find out there. Hydrex, Uflex has been around for a little while, and can also help slow down the rate of losses, whether it's through volatilization or denitrification. Now, so the question is, when should we use it? And I mentioned it a few minutes ago that our region plays a role here. Our regional conditions, climatic conditions play a role in how fast we lose nitrogen or how fast they can become available. For example, in BC, we've got high microbial populations. More degree days means more microbes. Similarly, in Ontario. So bacteria inhibiting products like the DCD will become a wiser choice. In Alberta, where we have higher pH soils, hydrolysis stabilizers are probably more effective where lower microbe populations exist, which I think we can expect. Long, cold winters and not particularly hot summers is what we can expect. Now, another form is organics, which I'm sure many of you are familiar with. Some of the products out there, while we used to have Milorganite available, now it's been replaced with Proscape. Earthworks is another one. A very safe, slow-release nitrogen source. It's only available through microbial activity or microbial breakdown. So again, won't be available in the spring or in the fall when temperatures are quite low. We need the soil to be active, so to speak, microbes active, so they can break it down. So that being said, these organic sources, whether it's chicken manure or pig manure, whatever you choose your carbon-based fertilizer upon, is very, very safe. Really, the only way you're going to kill or harm turf with it is if you pile it and it suffocates turf underneath it. So it's non-burning, very low analysis, typically around 6% nitrogen or less. It does have a great use. I used to use it on the golf course on short turf because in the fall, it's safe. You can put down as much as you want, and it would attract a little solar radiation. You know, they're typically dark brown or black, and that usually gave me a little bit of a kickstart in the springtime, attracting a little bit of sunlight and warming the soils up as fast as possible. Now, solubles are another type of fertilizer that we apply through our sprayer. Now, solubles are essentially just granulars. All we do is we melt them, or at least that's what it's commonly referred to in our sprayers and application tanks. So what we would typically apply a soluble at is very low rates. They only last at between 1 and a third of a pound being the maximum nitrogen, available nitrogen plant could take up at once. They only last for about 10 to 14 days. So very low rates, very low chance of leaching and losses. It's immediately available, and it's a good alternative, whether you want to water it in or spread it granularly. Watering it in usually allows a much more even application because the rates are so low. Typically, clubs will use this as a top-up on top of their regular fertility program. That is to say, if you have a granular regime where maybe you're applying a 3-1-3 ratio, but you've seen, like we have this last summer, very busy season, lots more play, lots more activity, and you find your turf grass is a little more stressed despite a program that would otherwise have worked very well. You can put down very low rates of solubles with your sprayer, get a very even coverage, and kind of top up the difference. As I mentioned before, nitrogen helps with recovery. So some of the solubles out there would be like your plant products, 20-20-20 or similar. Now, from what I used these solubles in my golf course management program, where I would add them with surfactants, wetting agents. Wetting agents typically draw water through the soil, and depending on which ones you're using. And so the solubles like this are quite compatible with many of the products. In fact, most of them. I would put them down with a surfactant primer, Revolution, and it would draw that soluble right down to the roots, make it immediately available. And as the last point, I should mention, solubles are root available, so not foliar. There's a big difference. Now, solubles can be anything. Can also be 4600 urea, very soluble, very high foliar absorption rate for urea specifically. Not some of these others. Urea, manganese being and iron being the very few that can get in through the leaf blade. Again, short duration, 10 to 14 days, very, very inexpensive, and have minimal temperature dependency, some of these. So that being said, if you were to apply it granularly, 4600 is quite dangerous because of the high salt index. It's very easy to burn. Not to mention, if we're going to apply a very high analysis, like almost 50% nitrogen on that plant, it's very hard to apply it evenly and safely because it's so concentrated. By melting it down and putting it through the sprayer, we can make sure that application is nice and even and consistent without having to worry about spreading one bag of urea across 4 or 5 acres, which was, from an operator standpoint, is practically impossible. Now, the next most important thing, and this will lead into our discussion in a moment, foliar feeding has gained popularity over the last few years because of its efficiency. It has a 76% absorption rate. So when we talk about losses of nitrogen being the biggest thorn in our side, foliar feeding can really circumvent all that. The idea behind it is you apply it to the leaf blade, let it dry on there, and movement through that upper epidermis and waxy cuticle is passive. It goes through by osmosis. So that movement of a liquid of high concentration to an area of low concentration is how that product gets in there. So really there's about 2% losses in foliar application, and we have also learned to combine them with chelated agents to help penetrate that waxy cuticle up top. So really the benefit of it is fewer losses, and therefore due to the absorption rate we can use very, very low rates. That is less than 1/10 of a pound, in fact 1/100th of a pound. So although they're a little bit more expensive in the grand scheme of things, we really get the fertility where we want it. Some of the foliar products out there that you might recognize, that the one that's been around for the longest, and I don't work for Griggs or make any money off of them, but I can vouch it's a very great product. The Gary Griggs line is a good example. You can see the Gary's Green, that 18-3-4 product, as an analysis. They also, what they do, that's their base, and what they would do is they would put a secondary in there. In this case, I'm using one of their products called Ultraplex, where you look at the analysis, a 1-0-14, and they suggest that you combine that. Well, what they're doing is creating a balanced fertilizer program. Combined, the two of them make basically call it a 19-3-19, which is really what we're gunning for as far as a balanced formula. So, and they're well designed, formulated accurately, so although it sometimes can cause a little complacency, a jug of this, a jug of that covers what most golf courses have as far as greens acreage, so it's been well thought out. Now the nice thing about foliars as well is they circumvent all of our soil problems. If I've mentioned before looking at the pH guide and seeing what available nutrients you're looking at depending on where you sit on that pH scale. What foliars basically do is they circumvent all of it, minimizing losses. You can literally, and that's why I took a picture of this. You can grow turf grass really, provided it doesn't dry out on pavement. It takes all the other concerns off your plate. In my past, I always used to use my foliars in the middle of the summer. That it was when, if I had a big tournament happening, or I had a very important outing, or whether it was a Pro-Am or PGA event, we got enough other things to worry about then, and we really wanted to get a good handle on green speed and whatnot in the middle of the summer for those big tournaments. So I would usually reserve my foliar applications to the critical points because they do tend to be a little bit more expensive, but you pay for that flexibility, or I should say, you pay for its convenience, and you can kind of sleep at night without having to worry about it. The next piece we're going to talk about is nitrogen deficiency. When we're planning our fertility programs, I recall saying earlier that all our fertility programs are based upon nitrogen first, phosphorus and potassium later. So just a few things to point out when and help you realize when your nitrogen might be getting a little bit low, and when you should start thinking about topping up. On the left-hand side, you can see a general chlorosis. It's a golf green, of course, and you can see kind of the patchiness of in this area here, and a darkness in the middle. Aesthetically not great. It does show a little more traffic has occurred up in this area and down here, so a good indication that nitrogen might be a little bit low and we're ready for a top up. Now on sports field parks, a little bit, or larger areas in general that don't get regular treatment, this is a fairy ring disease. Nothing at this stage, it's not too detrimental, other than aesthetically not great. So without having to spend a whole lot of money on controls, when you have this stage fairy ring on your playing surfaces, we typically will mask it with fertilizer. It's by far the cheapest way to control, and again, when you're up in the stands looking down on the field, you're not distracted by dark green rings, which is an expression of that fungus activity. Now, when we're looking at topping up or, for instance, masking that fairy ring or a little bit extra traffic that we may have received this month or last month, there's some quickly available nitrogen sources out there that you might recognize. Urea, of course, 4600, ammonium nitrate at 33%, ammonium sulfate at 2100, and ammonium sulfate is really considered one of the staples of industry, has a little bit of acidifying properties, so especially in Alberta when our pHs are a little bit higher, a great product to use as a monthly. Sodium nitrate, calcium nitrate, ammonium thiosulfate, among some of the others. So as far as slowly available nitrogen, these are the SRNs, urea formaldehyde, methylene urea, isobutylene diurea, that's IBDU, sulfur-coated ureas, the polymer-coated ureas, and of course organics as a bit of a summary of what we have available to us. So in all the research that you'll do about when to apply, what to apply, how to apply, the key behind all of it is on the image on the right here at the bottom. We want a consistent, even growth response. A failure of a fertility program is one that has the hills and valleys. You know, we in the image here, this is the sweet spot, the dark green. At the bottom of our chart here, we have too lean. We're probably seeing we have high disease potential. We have a poor recovery from traffic. Way up on this end, we're baling hay, and your staff are pissed off at you because you're raking, vacuuming, blowing clippings off endlessly. And really what this signifies, this upper echelon here, is you've wasted your money. We can't get it off fast enough. So a good reminder that we want to try to keep it consistent, right in the sweet spot, right in the middle, for whether you're a golf course application or sports strip application. From week to week, day to day, you want consistent playability of your surfaces. You don't want them to be growing an inch every 2 days without your ability to go and mow it in between. You've got two different teams playing two very different fields. So very important that we look at slow release nitrogen sources as opposed to quick release, unless you have the means like a sprayer on site where you can really micromanage, and that's perhaps some more common of golf course applications. So to reiterate, maximum quick release products are about 1/3 of a pound at a time. If you were to put down half a pound of urea, 4600, as itself, whether you melt it or otherwise, the plant's really only going to use about 1/3 of a pound at a time. So putting down more than that, you're getting into trouble. Monthly applications typically will range about 0.6 to a pound a month as required per recovery. So it's a lot of on-site evaluation of how that nitrogen's working for you. And of course, nitrogen and potassium should be balanced. So when I look at, or when I talk about a seasonal ratio, below there you see an approximation 3, 1, 3, 3 being nitrogen, phosphorus being at 1 pound, and potassium at 3 pounds is a good balanced way to start anyways as a target. Now, calculating fertility, and we won't spend too much time, we're not going to do math live like this, but I will walk through it fairly quickly for you. You know, I tell my students that if I ever had a tattoo, it would be rate divided by analysis. That's for turf nerds like me, that's the one formula that you should never forget. Rate meaning the rate of nitrogen per 1,000 square feet that you'd apply, whether it's 1/3 of a pound or a pound at a time, divided by the analysis, which is the percentage of nitrogen in that bag. You divide rate by analysis, gives you the total product that you need to apply per 1,000 square feet. That's total product to get that rate you're looking for. And when you're adding up your total applications, you know, you're not always going to be using a 4600 or 2100. There's oftentimes phosphorus and potassium in there. The simplest way to determine how much potassium and phosphorus you put down is after you've done that rate divided by analysis formula, you have a total product multiplied times the other percentage of phosphorus and percentage of potassium in the bag to get where you're, how much you've put down. Now, foliar treatments, on the other hand, are a little bit different. As I mentioned, they're gaining popularity due to the minimal losses and low rates that we can put down. Rates are quite consistent and predictable, and having mentioned earlier, we basically bypass all our problems. On a 2-week cycle, you can worry about bigger things like booking that big tournament or dealing with staff. It can take the load off for a period of time. Now, foliar rates, not to be confused with soluble. Soluble rates are usually double that of foliar rates. So foliar rates being 0.02 to 0.0 pounds of nitrogen per 1,000 square feet every 2 weeks is about right, 10 to 14 days. They're quite compatible with most fungicides and herbicides, although I do recommend the jar test. Put the two products together and give them a shake and see what happens. On the most extreme cases, you'll have products heat up, have a chemical reaction, which obviously is not good. But calculations are similar to foliar calculations, or foliar fertilizer calculations rather, are very similar to a granular with one exception. What we've got to do when we're figuring out foliar rates is figure out their net weight per pound or per ounce. And again, without wasting too much of your time going through mathematics, it's still rate divided by analysis, but your analysis needs to be multiplied by the weight of the product. If you want to calibrate per ounces or you want to base it on pounds, this is the one option, basing your rate on pounds of nitrogen. That is to say, you're deciding that you want to put down 0.5 of a pound, and you can figure it out that way. The alternative, of course, and I'm assuming you have time to go back and have a look at this later. Once you have a calculator or you produce one using Excel, you don't have to do this too often. But the other alternative, and what I find is there are quite a few professionals out there in industry that are becoming more and more complacent about the rates they're applying and when and why. They're following label rates, fair enough, but when asked how much nitrogen did you just put down, many aren't really that aware. So I would hope that everybody takes a professional approach to all this and look at those application rates to really make sure you know how much you're treating. This is just the other option. If you're basing your application on recommended label rates, make sure you know what your rate of nitrogen is. And again, all we're doing is finding out how much nitrogen is in that that gallon, and multiplying it times the number of ounces that the label is requesting you to apply it at. So, granular or foliar, how do we choose how much nitrogen and how much potassium should we be applying? Now, some of you may have heard me speak before, and maybe even on this topic. We're going to dig into kind of how, and wrap all this up and bring it all to light here. Fertility is particularly important when we're trying to get our playing surfaces through the winter as healthy as possible, and to come through into the spring as healthy as possible too. And for many years, the application of nitrogen and potassium in the fall was a bit of a guessing game. You know, the principle behind carbohydrate storage was that idea, like the hibernating bear. If you fill it full of energy, when in the absence of light, it's not photosynthesizing anymore, therefore needs to burn through that energy in order to get through. And if you don't give it enough energy to live throughout that respire through the wintertime, you're going to have a terrible spring. So for many years, turfgrass managers would apply fall treatments of nitrogen during that hardening process in attempts to pack carbohydrate. And we know it worked. This is a perfect example of a healthy grain coming out of winter after being packed full of carbohydrate in the fall. The thing is, though, we never really had enough research to prove how much we should be applying, why is it so successful, and so we took on some research projects to try to determine what was really going on. Now, as far as fall hardening and fall fertility goes, there was some conflicting information. Way back in 3943, we found a correlation between more nitrogen in the fall, increasing crown hydration, and subsequently decreased winter survival. As time went on, we found fall applied nitrogen stimulated rooting, photosynthesis. You know, when we apply fertilizers in the fall and our grass stays nice and green. The expression of chlorophyll implies that, yeah, the plant's still working, it's still using it. Even though we're not mowing it off, it's still being useful. So what our opinions or theories were that we were packing carbohydrate. In 1980, the research was done that determined potassium levels were correlating to cold temperature tolerance, which had, of course, set the ball rolling. Well, maybe nitrogen and potassium work together. And looking at both carbohydrate and low temperature tolerance and our susceptibility to winter injury, the most recent research, aside from our own, was to examine the effects of granular applications of nitrogen and potassium on survival and spring green up of our turf. So, bringing this back to home, Olds College of Prairie Turfgrass Research Center took on some research in 2013 on granular fertility, and then followed up with a foliar trial that we just finished. So I'm going to share with you our findings and some of the conclusions. The objective way back when, using the granular study, was to determine appropriate ratios of fall-applied nitrogen and potassium and their effect on cold hardiness. It was a granular study in 2013. And what the study entailed, and if you haven't been there before, on the right-hand side is our turfgrass plots at the Prairie Turf Research Foundation. The biweekly applications of ammonium, nitrate, and sulfate of potash. There was 128 treatments granularly of N and K, and you can see everything in green on that image is nitrogen applications, and everything in orange are the potassium applications. You can see what we were trying to do, hopefully, using low to high potassium, blending the two, finding out what was going to work the best in terms of communicating to you, the turf manager, what the best ratio of N and K would be to ensure winter survival. So the methodology included early hardening, LT50 testing, that's lethal temperature testing, where we tested each sample from each plot or treatment into a controlled environment and determined what temperature killed half of the population. That's lethal temperature to kill half the turfgrass population. We also measured crown moisture. We took tissue and soil tests and compared spring recovery that data with our spring recovery data in density and NDVI, which is essentially color. Now the tissue, percent tissue results, we took tissue tests of everything, and after 2 years proved a consistent ratio, but the tissue test in year 2 proved less accumulative nitrogen and potassium. So the maximum nitrogen percentage we could get in there was about 4.3%, which is that was having applied a pound of nitrogen in the fall. And the max potassium was 4.1% at a half a pound of potassium in the fall. So to give from a granular study, it was a great advancement to see this was appropriate ratios of N and K. Basically, call it 2 to 1 or 1 to 1/2. Now this is how we looked at spring recovery after pulling the plugs out after springtime. We would separate them and grow them out, and you can see on the right there, this is how we determined the survivability. And you can't really see the numbers along the side of the trays there, but they would gradually go. You can see that first row was essentially control, and everything behind it would be -2, -4, -6, -10, -12, and so on. So we found in that first and second year study of the granular study that increased nitrogen treatments improved spring color, and potassium alone didn't promote spring recovery at all, but combined, the quality ratings did improve, which did show an interaction between N and K that was kind of hard to ignore. So from a granular or a conclusion point of view, there was a correlation when N and K were applied together. Taking the study to our research to another level here, we proved a relationship that those two needed to be applied together, and a maximum of half a pound of potassium was sufficient in terms of spring recovery and winter survival. So previously, there's been lots of turf managers out there that throw the kitchen sink at it. 2, 3, 4 pounds of K, we didn't find any increased advantage to applying more than half a pound of potassium when it was applied with nitrogen. Now that said, an ideal ratio of 2 pounds of nitrogen to 1 pound of potassium, or 1 pound to a half applied in fall, was viewed as maximum hardiness. So cold temperature tolerance was also maximized at tissue levels of 0.2 to 3%, and potassium tissue levels went from 1.9 to 2.5. So there was a relationship that we discovered in this first granular study, but it did raise a question: could we increase the tissue content of in the plant of that N and K to increase fall hardiness by using foliar treatments? So of course this prompted the next stage of the study, which we just completed at the Research Foundation: fall applications of foliar applied nitrogen and potassium and their effect on winter hardiness. Now this was funded by the Canadian Turf Research Foundation, and we proceeded through that program at that project at the Prairie Turf Research Foundation. Our initial principal investigator there was Katie Dodson, who's now working for Syngenta, our lead technician, Mark Anderson, and myself. So the foliar trial summary here, as I mentioned before, industries has been adopting foliar nutrition or applications quickly the last little while. And so we're trying to take that trend and apply some of this research to it to find out whether or not foliar applications in the fall are worthwhile, worth it, or a good approach to getting through the winter. What our hypothesis was that due to the 76% absorption rate, less than 2% losses, that foliar application in the fall would, and its previous research proving that foliar applications were more effective and more rapidly absorbed in the fall rather than the spring. The hypothesis was that we could get greater absorption, therefore increase the percentage of nitrogen and potassium in the plant, thereby packing more carbohydrate, where potassium was responsible, or has been proven responsible for cold temperature tolerance. We could maximize them and try to give our turf the best opportunity to get through the wintertime through foliar treatments. So that was the principle behind the hypothesis and why we undertook this this project. So what we applied it on is we used a USGA spec annual bluegrass green. There's lots of previous research done on creeping bentgrass, so we took it on annual bluegrass. Many facilities out there using Poa annua. We fertilized biweekly in 4 replications. That is to say, we applied the same thing 4 times to ensure that we minimize any problems in application or to ensure consistency. So we used a urea ammonium nitrate product at 2800, and potassium was 0029 potassium acetate. Our application dates were August 20th, September 1st, September 17th, and October 1st, based on that foliar treatment of 10 to 14 day interval that we've talked about before. Now, after the first year data, which was quite exhaustive, no statistical difference among nitrogen and potassium treatments were found. However, we did confirm that interaction between N and K, where when nitrogen was applied with potassium, it did result in greater temperature tolerance. So we can confirm that the two need to be applied together, not just one or the other. In looking at cold temperature tolerance, we found where nitrogen was low and potassium was at the low rate at 0.25, greater cold temperature tolerance resulted. So not to dwell on it too much, low rate of N it was a quarter pound, and low rate of K was a quarter pound. They're balanced 1 to 1. And I think that's the important message to remember here. High rates of nitrogen and or potassium resulted in lower temperature tolerance. So that being said, too much of a good thing can, or there can be too much of a good thing, I should say. So don't throw the kitchen sink at it. 5 pounds of nitrogen, 5 pounds of potassium is going to do more damage than good. So we're going to talk a little bit more about it, but anyway, just to make that clear. Now, some discussion about lethal temperature tolerance, or the LT50 of that poa annua. The species that we used is annual bluegrass. It was a true putt variety out of Oregon, so, or the reptans, creeping bluegrass variety. So if you look at the chart on the right with terms of the treatments and follow that orange line, it shows the best fit line, or average temperature, which is roughly around 10 to minus 10, give or take. It does show a bit of a limitation. And remember, the applications there of N and K are all over the map. So that average best fit line really shows lethal temperature on an average for all those treatments. And when, just to point out, although minus 10 doesn't seem particularly cold, if we consider our turf species under cover of snow, the temperature underneath snow only ranges between about -2 to sometimes +2. So it would be, without a tarp on it, without any snow cover, it would be far more likely for that temperature to drop, especially in Alberta, and that annual bluegrass see -20 or even -30 that we've had out here before. But typically, if you cover it, or you have good snow cover, temperatures are never going to get down to that lethal temperature. So the takeaway here is, if you do have annual bluegrass playing surfaces, or you're trying to save the POA, keeping them covered, whether it's tarping or insulators or snowfall, call it snow fences or otherwise, crucially important if you're using annual bluegrass or trying to keep it alive. Tissue percent and cold tolerance after year 1. This is a scatter plot on the right showing kind of a weak correlation between nitrogen and potassium tissue content. However, it did prove that the two nutrients were dependent upon each other for nutrient uptake. Now in year 2, the second year of the study, there's our technician Mark Anderson. The statistical indifference of a two-factor analysis that we took on in the first year would force us to kind of adjust our methodology. So we reduced the plots from 120 to 64. 16 treatments instead of 32 would concentrate the project scope onto those parameters that we've identified and wanting to narrow. So the LT50 process continued November 18th during the hardening stage, January 21st, presuming that was fully hardened, and April 21st in the springtime during the dehardening process. And to wrap, to give you a good look at what those applications looked like, these are essentially how we put it down: low, medium, and high rate of nitrogen and potassium, and we basically played the round robin between low rates of N to high rates of K, and every combination in between to try to determine correlation. Now, application phase temperatures. Of course, we want to check to see how our temperatures fluctuated in the fall, just to see if this played some kind of a bearing in the absorption of a nutrient applied. Between the third and fourth application, we had a temperature drop down below 0, which presumably translocation drops when the plant's not actively growing. Same sort of reasoning why we don't apply herbicides when the weather's too cold, because the plant's not actively taking it up. So we did, in terms of considerations, what may have skewed the data or had an effect on it. This is something that to communicate, not anything we can control, but interesting nonetheless. So fall color retention. This is an image of the plots in the fall. We did see some significant difference here. Obviously, you can see from the picture there, different rates of N applied alone or in combination with K had a significant effect. Chlorophyll expression suggests that carbohydrate storage was happening. That's that expression, the green, the chlorophyll. But again, potassium, and you can see many of those plots that showed no expression, those were typically potassium applications without a combination of nitrogen with them. So K applications above their respective nitrogen applications produce slightly negative response, in fact. So higher potassium than nitrogen proved detrimental. So the tissue analysis percentage, we look at nitrogen in the data that we got back from the second year study. Our nitrogen ranges went from 2.7 to 3.55, showing gradual increase the more nitrogen we put down. K, on the other hand, you can see only a percentage range from 1.7 to 2.0 was statistically indifferent. Not great uptake. We were hoping to get more than 2. In the granular study beforehand, it showed the greatest cold temperature tolerance when percentage of potassium rates were higher than 2, and we got as close to 4 with granular applications. So percent nitrogen tissues did increase with the rate, but K not so much. What it does imply is that absorption of nitrogen by foliar sources in the fall is possible, is feasible. We did see, despite that drop in temperature between 3rd or 4th and 5th applications there, still absorbed. Absorption through the K, however, proved less effective. So when we look at treatments of combined N and a mid to high rate of K, this produced the highest tissue content of both. So in our studies, we basically were able to see that there was a positive reaction of the two, but we didn't get as much of a kick out of the potassium as we wanted. Now, when we looked at the cold temperature tolerance of those two applications, November 18th, 21st, and April, those 3 sets of LT50s that we took, look at how close that temperature range is. -7 to 8.5, and each of those during the acclimation process, fully acclimated, and in the spring, that's maximum survivability after the foliar study, which I found particularly interesting. So with that regard, not statistically different in terms of cold temperature tolerance amongst those 3 sets in all those samples. So it is interesting, and perhaps we've reached that physiological barrier that the poiannuus simply can't survive, regardless of what you put down, beyond about -8. So the summary, average cold temperature tolerance of year 1 and 2 foliar studies was about 10 degrees into the negative. This expressed less cold hardiness than the granular study of -13. So, which is interesting. Increased likelihood of annual bluegrass had reached physiological limits. Not related to N and K, but granular results did show modest improvement. So with POA's poor low temperature tolerance of the annual varieties, it ranged from about -10 to -13. And as I mentioned before, regional and local perennial varieties might be more adapted to our colder temperatures than that first-year Oregon-based source. So essentially here at the end of the day, the takeaway is if you're trying to grow POA, you've got to balance N and K to 1 to 1/2 or 1 to 1. And but more importantly, in terms of cold temperature tolerance, you've got to keep that POA from dropping below about -10, regardless of what you choose to apply. So fully POA or surfaces, you need to make sure that you get a good snow cover on there. Keep those temperatures relatively close to 0, or you risk turf loss. Spring color ratings here, applications of N at 1 pound and 1.5 were not really statistically different, suggesting that any more than about 1 pound might not be necessary. They did, the higher applications of rate, though, up to that 1 point, did show improvement. So up to 1 pound is sufficient in terms of fall applications of nitrogen. Conclusions. To finish all this up, nitrogen and potassium applied together are necessary to maximize cold temperature tolerance and will produce the preferred spring green up when ratios are 1 pound of nitrogen to 1/2 pound of potassium, up to 1 to 1 NNK. Foliar treatments can be urea-based, sprayed foliar, and will accumulate in the fall despite dropping temperatures, while foliar potassium is less mobile. Where maximum cold hardiness was achieved in the granular study at -13, when tissue content was at 3.9, our foliar study only made it to 2.0. So this implies that foliar absorption of potassium is less effective than the granular sources, and perhaps that has something to do with soil temperature, ambient temperatures, Nonetheless, this was our findings. Well, this concludes my presentation today on advanced fertility and current research at the Prairie Turfgrass Research Center. Thank you so much for joining me today, and enjoy the remainder of the virtual conference.